Welcome to the Gridwise Architecture Council's video library. I'm your host, Ron Bernstein, and chair of the council. The following presentation was given at a face-to-face meeting in Knoxville, Tennessee on October 4th, 2023. Our presenter is Melanie Johnson of the U.S. Army Corps of Engineers, and the title of her presentation is Army Microgrid Implementation and Criteria Development. Please welcome Melanie Johnson.
So thank you, Melanie, for joining us today. We very much appreciate it. We're looking forward to hearing your presentation on Army Microgrid implementation and criteria development. Please welcome Melanie.
Morning. I'm glad to join you this morning. It's been a little while since I last spoke with this group, so I'm going to, what I'm going to try to talk to you about this morning is kind of where the Army is in terms of why we're deploying microgrids, the sort of plan and schedule, and some of the motivations for doing that, and then jump into some of the standards, criteria, and things like that that we're developing in order to enable us to do this sort of in a consistent way and get, reliable results for our installations. There's been a lot of effort over the years to try to improve an installation's energy security. That was sort of the original words in the world that I came into, and now we've moved to this idea of energy resilience. But what you'll find actually at the installations is a lot of different projects that were done at different times by different parties, and there's not a lot of coordination between them. You might find some really large-scale solar, but it can't talk to anything else. It's isolated. It might be aging, it might be new. It'll depend on the installation you visit. You may find some limited microgrid demonstrations or small microgrids that were built as demonstration scale projects. They exist in very closed, restricted networks, and that's still our paradigm for implementing microgrids, and they can't talk to anything else. So they may or may not be able to use the utility scale solar, or they may be completely cut off from it. And you're not going to find a lot of crosstalk between our energy control systems, right? If you have a building automation system, UMCS, that's not going to be talking to any of our other energy infrastructure, right? It's not going to be communicating with a microgrid. And so the result is that our installations remain very grid dependent. Most of the renewables we have are still just grid tied renewables. We have really limited ability to island from the grid and pretty much no ability to participate in an energy market other than with a human in the loop, like by phone call. Our resources in these installations are isolated from one another. We mentioned the closed restricted networks. In a lot of cases, we don't have the required cybersecurity certifications to bring those onto our more connected, less isolated networks. And you'll find a lot of just single generators connected to single buildings. And because there's no interconnection between these control systems, the visibility into them is limited. You may even encounter situations where to access any particular one of these systems, you have to go find a whole different laptop that's allowed to be on the network that the system is on. So we don't have integrated user interfaces or even integrated terminals where you can flip between all of these different systems. And we have really minimal SCADA coverage in our installations as well. So this isn't a great situation. It doesn't help us have great energy awareness by any stretch of the imagination, and it really limits our ability to use the power that we can generate where we want it, when we want it. And so a lot of the goals of what we're trying to do now are, yes, to implement microgrids so our installations can island, but we're trying to fix a lot of these problems too. So why is the Army building microgrids? Well, the requirements we place on infrastructure in the Army are quickly outpacing our existing capabilities, right? We have loads and missions that require really exceptional power quality and reliability. We have built out a lot of distributed generation without really much coordination or care about where we put it. We have requirements for security postures and a resilience requirement that requires our installations to operate islanded for 14 days. And that's not really possible without a coordinated plan. And in the last year, we've seen new requirements for electric vehicles and other electrification for our buildings and other mission loads. So all of this means that our distribution systems on installations are going to face increasing challenges as we move forward. But at least in the last few years, we've seen policy try to catch up to these requirements, right? Recent, Army-specific policy has started to recognize that we have to do something about this, that if we're going to say our installations are going to have energy resilience, we need to actually make a plan to do that. And I think all of that sort of culminates in this Army climate strategy from 2022, where the top #1 requirement was that every installation have a microgrid. So we'll talk about that in more detail in just a second. And we've also started seeing language in the National Defense Authorization Act, which is the appropriations bill from Congress that defines what the DoD will be doing in the last 2 iterations. And as you're all aware, FY24 is to be determined. Okay. That Army climate strategy from 2022, the first objective listed in the document is that we install a microgrid at every installation by 2035. If you read a little further into the document, you'll see that that requires us to build 130 installation scale microgrids worldwide, with priority for those microgrids given to installations with mission assurance. So that's something the Army has to be able to do. Installations that allow the Army to mobilize forces and project that force into wherever the Army is actually performing missions, and power projection platforms, which is another way of saying how we mobilize things, how we get things into the field where we need them. There's a report that you can find online. I put links down here at the bottom of the slide called the Annual Army Energy Consumption Report. And if you dig into that a little bit, you will find that in FY22, the Army consumed roughly 10.7 terawatt hours of electricity at our installations. That's roughly 29 gigawatt hours per day. Keep that number in mind for a second. We have another piece of policy. This is just an Army directive. It's not legislation, but this is where that 14-day energy resilience requirement comes from. Our critical missions have to be sustained for 14 days during a utility outage. And this also targets our water sustainability in an outage, but water is too hard. I'm going to stick with electricity. So if we do some really back of the envelope math, we arrive at this idea that our microgrids need to have about 410 gigawatt hours of energy reserves to meet that requirement. Now, there's a little squishiness here, right? Not all missions are essential. Not all missions are critical, and the amount of energy they're going to require is going to fluctuate on an annual basis. So I'm lumping everything together and just taking really basic averages to get to this number, but I still think it's a very interesting indicator of the scale of the problem. So as of February 2023, when we started doing surveys about what we actually have, we found that the Army right now has about 10 kind of microgrids that contribute to these requirements. There are others that have fallen out of operations or weren't sustained or were meant to be demonstrations, and so they haven't continued to operate past their demonstration. So we have about 10 that are somewhat functional and contributing to this requirement. That's a really big leap to get from 10 to 130. So there's another piece of policy that followed the climate strategy called the Army Climate Strategy Implementation Plan. And it lays out how are we going to meet the objectives that are in that climate strategy. So in FY24, we're supposed to have 20 microgrid projects in design or under construction. We've met that goal already. So we just started FY24 a couple of days ago, and there are already this many projects, more than that actually, in process within the Army. We are supposed to have 15 additional operational microgrids by the end of FY26. Another 20 in FY27, and we're supposed to have 30% coverage of critical mission demand by 2027, and 50% coverage of prioritized demand. And what those mean is determined at higher levels of the Army than where I sit, but it's still a lot of load. So to make all of this happen, we're really relying on 2 main kinds of funding. The first is a program called the Energy Resilience and Conservation Investment Program, or the ERSIP program. This provides a kind of a color of money called military construction dollars for energy resilience projects. And it comes with some loosening of different rules surrounding military construction appropriations that let us do these projects that don't have a return on investment. You know, energy resilience is not necessarily there to make to generate a revenue stream or pay back, and so the rules in this program recognize that fact. We also have some mechanisms that allow us to use third-party financing from private industry as energy savings performance contracting or utility savings contracting, and all three of these programs are managed by the Corps of Engineers. So we are going to be building these systems for the Army. Okay, so a little more specifically, the process and procedure for how we're going to get this done is in this sort of graphic at the bottom. So our microgrid concepts actually come from a variety of sources, people, and organizations, but generally an installation will have some sort of study done. This is most typically a study called an Installation Energy and Water Plan, an IEWP. And in that, a specialized team, we have one at Searle, there are others, goes out to the installation and kind of evaluates its current status. They look at, you know, where are the critical missions, how are those served, do they have any backup power, are there any regions within the installation where there's a concentration of critical loads where we could implement a microgrid. And at the end of that report, they make some recommendations on potential projects. That report is generally pretty vague. It's not going to have a lot of details. It's sort of like drawing a circle on a map and saying, like, this looks like a pretty good area based on a quick glance. So they're supposed to base it off of one of those evaluations and work with a lab or an FFRDC, maybe a DOE lab. We have a few other organizations within DoD that can help installations do this to come up with a microgrid conceptual design. That conceptual design gets documented in a very formal way in a document called a DD 1391. And all that is a sort of project scope definition, and it's what Congress approves for us to use appropriated money. I realize all this appropriations and money stuff is probably boring, but it actually plays a big role in how we do these projects and what we're allowed to do and when, and a lot of the rules, which is why it becomes really relevant even when we're coming at it from a technical engineering angle. So those 1391s are then submitted to the Corps of Engineers, and we review them and validate them to make sure that the project is feasible. We are still figuring out what all we have to do in order to determine if a microgrid project is feasible for an installation. It's interesting to note that our installations do not necessarily have great data on their infrastructure. We can go out to an installation and find that they have a very recent modernized distribution system with a fantastic detailed one line with all of the information you could possibly want. And we go to some installations and they're like, here is a block diagram that we drew in PowerPoint. And it doesn't have any nameplate data in it at all. So it can be very different depending on the installation we're working with. Many of our installations have privatized their distribution system, so they're actually owned by a third party, and that third party's perspective and opinion on how much they want to share with us, how much they're willing to open up and let us look into their system operation can really change how much we're able to validate the project scopes. So it's a whole procedure. It takes about a year for us to work through each FY's class of validation projects, and then they are submitted up to the higher the Office of the Secretary of Defense, sort of a joint service level where they're down selected. Ones that are funded are back to us, and we send them off to an A&E design firm for 100% design. So all of that is happening between the Corps of Engineers, Huntsville Engineering Center, my laboratory, ERDIC Searle, and another part of the Corps of Engineers called the Power Reliability Enhancement Program. And they're an interesting story in and of themselves, but their original mission was extremely high power reliability for like mission silos and other kind of post-nuclear apocalypse kind of assets. So they're a really interesting organization. From there, we move into construction, and then we're into this area that we haven't ever really executed, like testing and commissioning, and then finally sustainment. So those are all still open questions. All right, so that's a whole lot of procedure and process. To make all of that easier, we are currently working on 3 major criteria and efforts to make all of this easier. The first of these is a unified facilities criteria called installation microgrid design. We have the newly minted MIL Standard 3071, Tactical Microgrid Communications and Control, and we have a Unified Facilities Guide specification for microgrid controllers. So we'll talk about each one of these in a little more detail. But before we jump into those standards, some sort of high level, what are we prioritizing when we are designing microgrids for an installation? The first is that we have to clearly define the objective. What is this microgrid's purpose? What missions does it serve? What buildings do those missions live in? What are their loads look like? And what's the threat that this microgrid addresses? Is it severe weather? Is it regional grid instability? Or like where they exist in the grid is at the end of some long transmission line, and so they're at risk if that line in particular is affected by any kind of event. Are we looking at other kinds of threats? Some of our installations, right, are on islands. They're in very small power systems, and so they can have a lot of impact on the commercial utility that serves them. We also really try to limit artificial constraints on our design. In some of the initial microgrid work within DoD for optics or to get people's support, they would commit certain resources to being in the microgrid, or say it has to serve this particular mission, or it's going to be on this base, even though this base doesn't have what we're looking for a microgrid site. So we've tried to get away from bounding the problem before we even get started for non-technical reasons. We also don't want to do any harm to the existing backup situation of the installation, right? We want everything they already have to maintain its functionality as much as possible. And our microgrid layer should improve reliability, not go the other direction, which is one of the things we're trying to come up with a good way to prove that for each project in a way that doesn't cost a whole nother project's worth of funding. We try to make maintainable choices, right? So each installation comes with its own existing distribution system, its own equipment that it's familiar with, and their operations staff are ready to maintain. They have certain networking equipment that they use, and that their network command center is used to dealing with. And so we try to use that same kind of equipment for each installation so that there's not a learning curve on that piece, right? Because the microgrid control system is going to be enough of a learning curve for our operations staff as it is. And finally, we have to define and document the who, what, when, and how is this microgrid going to work, right? When does it turn on? Who starts it? Why do they start it? Who do they contact when they start it? How long does it run? Who makes the decision to go back to utility power? Is that all automated, or is there a human in the loop? There's a lot of questions that each installation has to kind of analyze and figure out what their best operating procedure is, and we have to document that even as we develop the design. Okay, so the whole purpose of all of this is that, you know, when we lose the utility, maybe we have a central plant, some utility scale renewable resources, energy storage that can continue to support the installation. If we degrade further, maybe our distribution system is degraded because of severe weather, we can fall back to some networked backup power generators. And if that even fails and our microgrid is gone completely, we are back to single facility generation that supports the most critical missions on the installation. So that's really the goal, and where we are trying to move our installations to a paradigm that looks more like that, borrowing very much from this idea of defense in depth from the cybersecurity community. Okay, so now into these standards. So the Resilient Installation Microgrid Design UFC, it is a completed draft. It is currently being staffed for signature in the joint services. That kind of process takes a very long time, as each service has their own review procedure and who signs first, who signs last. It's a bureaucratic nightmare. But what this facilities criteria is focused on is designed requirements, performance metrics, the sequence of operations, guidance on commissioning and validation and sustainment for microgrids on installations. So the idea here is to provide an engineer who has been handed the DD 1391, and it says, here, this is the microgrid you're going to design. Here are its major generation components, and they have to translate that into a request for proposal, right? So they have to kind of have an idea of what they're looking for. What are the requirements going to be? When they get a proposal back from that contractor, what should they be evaluating that proposal for? So it's intended to provide some guidelines and basis and some education for those engineers to make good choices and develop microgrid designs that are feasible and consistent with the requirements they've been handed. So what we tried to do with this is create a document that allows for performance-based design. So not necessarily saying install, brand A generator of this size over there and put the switch here. We're trying to be less specific than that, right? We want to be able to say, we need to design a microgrid that will support buildings A, B, and C for 14 days. Buildings D and E are a priority for us to support, but they can be shed under the most critical conditions. And then we have a bunch of nice to have loads that we would like to support when conditions allow. Or we need a microgrid that includes this large solar array that we already have, or will integrate with our third-party owned CHP plant. So rather than get very specific about where equipment goes or which equipment it's going to be, we're trying to give more performance-based requirements for our design contractors. The UFC relies on service-specific policy and mission requirements to inform those performance requirements. So each service has their own guidelines, their own objectives, their own, like the Army has the 14-day resilience requirement. The other two don't necessarily have that, although the services tend to eventually get to the same point. And so you'll find in the UFC that there's very flexible guidance so that the Air Force can substitute in their current requirements. The Navy can put theirs, and Army can put whatever they need to have. We have done our very best to create this criteria in a way that does not specify a particular microgrid architecture, right? It's not going to say you have to have distributed generation. It's going to say you have options. You can have a central generation plant. You can have distributed generation along a feeder. You can have facility located generation. It offers a lot of different design options so that the engineer working on the system can tailor it to what that installation requires. It also does not attempt to say like what kind of acquisition this microgrid should go through. Again, each service is going to have its own preferences. Right now, the Army does a design, right? And we stop, and then we go out and we compete the project for construction. So the designer is excluded from being the construction contractor, and we get a whole new one. It's called design, bid, build. But I think Air Force still does design build, where the two things are contracted together. So it allows for both in terms of how we structure the design and all the different stop points that could be included in that design process. We also look at, it emphasizes and tries to encourage that idea of defense in depth and layering different backup systems. There's competing schools of thought within the DoD microgrid community, right? One school of thought is mine, and that defense in depth concept, where we don't pull out existing generation. We are trying to network existing generation or add either that sort of networked generation layer or the installation layer generation systems that can provide an additional layer of reliability for the critical loads. The contrary school of thought is, well, for maintenance and sustainment and total cost, you should rip all of that out. All of that existing stuff should go, because you shouldn't maintain it any longer, because you're only adding costs if you do. If you keep the old stuff and have to maintain it, and you add a layer, you have to maintain that. And I mean, The USC definitely went with the defense in depth perspective because many of our installations distribution systems have not been particularly hardened against the threats the microgrids are trying to address. So if you're trying to address like a severe weather threat, the distribution system could still primarily be above ground and pole mounted rather than already being underground. And so we're wary of removing geographically co-located generation from critical loads because the distribution system is still so exposed. Hopefully that will change and evolve as we go on, but sometimes you start to wonder, like, should we be investing this in a microgrid or should we be hardening our system in other ways? Okay, so finally, it provides some guidance and considerations for measurement and validation, as well as operations and maintenance. So for planning for those and what should our installations expect when they receive a microgrid project. I can stop and let you guys question me here, or I can run through the other two. I feel like I'm doing a lot of talking. What's the preference?
Keep the same questions to the end, if that's okay with you.
Yeah, that sounds fine. I'm going to go into even more detail about this UFC because it's the most developed product we have. So sort of the technical requirements you'll find in this UFC and what will qualify you as a DoD microgrid is that your system has to be a bounded system with autonomous controls, right? It has to be able to operate by itself, and we have to be able to say, like, and here's the boundary of the microgrid. It has to be capable of islanding with the ability to parallel and network more than one generation source. It does not necessarily have to contain more than one generation source, but it must be able to integrate at least two. It has to be capable of grid autonomous black start. So if you're not a microgrid, if you can't start from a dark condition, it has to be able to do system balancing, right? It has to be able to maintain generation and load balance within its boundaries. We have to have sufficient generation to meet the peak critical load within that bounded system, and it has to be able to provide that, it has to be able to support the critical load within its boundary for that duration as required by service policy. So for the Army, 14 days. And we want, here's that defense in depth concept, fail-safe operation. If something happens in the microgrid and it fails, all the existing generation should revert to that dedicated single facility operation that we currently have. It must be able to achieve a cybersecurity authority to operate accreditation based on whatever service and whatever chain of command you're in. And it has to use commercial off-the-shelf technology to be considered a permanent infrastructure improvement. You'll find in a lot of the early DoD microgrid demonstrations, we used a lot of really developmental and emerging technology, and that has posed huge challenges in sustainment. So it has to meet all of its requirements without any of those emerging technologies. Although you can still put them in there, it's just they don't, you have to be able to meet your requirements without them. Okay, if you want to exceed the technical criteria in the UFC, we offer some options like for blinkless transition. So this is like energy storage supporting critical loads so that they don't experience any sort of interruption when transferring to and from islanded operation. You can include energy storage. Energy storage is a very controversial topic within much of the DoD. So there are some, the UFC for energy storage says that any grid scale lithium ion batteries cannot be placed in a occupied facility, nor can they be placed within 100 feet of an occupied facility. And so figuring out where to site them within some of our more space-constrained installation has proved to be pretty challenging. And so we didn't want to require, there was a group during the discussions for this saying, like, you have to contain energy storage to be a microgrid. No, you don't have to. It's nice to have, but you don't have to. We have to have two, so these are, again, exceed the minimum criteria kind of options, right? Having more than one grid forming asset having more than one human machine interface, like for a visual front end, having more than one black start source, being able to load shed based on some prioritized load shedding scheme. And this one may surprise you, but grid connected operation is considered exceeding the criteria. That one arises from the fact that many installations, particularly within the Navy, are on very small islands, and they are the grid for the island. And so they're going like, well, you can't require us to connect to a utility grid. We are the utility grid. So it's a little bit of a semantics, I think, but that's where it ended up. So just a little bit more on this idea of fail-safe operation. The layers that the UFC cites and considers are a little different than the ones that I put in my slides, where the UPS for the critical mission load is the bottom layer, geographically co-located like spot generation, the backup generator that sits behind the building is the next layer, a networked microgrid where those generators are working in tandem to support a group of critical loads would be layer 3, and then the external utility is layer 4. So the idea here is that when something bad happens, whether it's loss of communication within the microgrid, some sort of fault in the microgrid's distribution system, or anything else, we can fall back down those layers so that the critical loads still receive power. All right, moving to the tactical microgrid standard. From here out, we have a lot less detail. So MIL Standard 3071 was developed for tactical systems. These are deployed power systems that are basically a pile of equipment that are shipped into DoD operating theaters. They're built by soldiers. We're not talking about something that's highly planned. This is like they brought in 3 generators and a pile of cables, and they have these boxes called P-dice, where you feed in all the cables and you feed in the generators, and those are basically like your switching stations for the little distribution system they will build. The original MIL Standard 3071 targets only user voltage microgrids. So these are microgrids at 120 volts. The reason for that is that they don't take magnetics into the field. They're too heavy. There's lots of work going on to kind of fix some of these issues, right? Like you don't have to take a magnetic transformer anymore, right? You can work on developing solid state transformers. So that's definitely an area of research in this field. DC microgrids are another huge thing that's an area of development in these tactical systems. Even vehicle-centric microgrids, where it's really vehicles are the generators. They have auxiliary power units that are able to provide a lot of additional electricity just off the vehicle's engine. So as well, sorry, I apologize. I am mincing up my words this morning, but with the vehicle's engine acting as the generator, basically, with that APU. So this is a very different use case than an installation scale, grid scale microgrid. However, the final MIL Standard 3071 is primarily a communication standard, right? It defines protocols and interfaces for different microgrid equipment to communicate with each other. It comes with a full point schedule for that communications protocol, and in its final iterations, the folks developing this said, let's make sure that it just covers any microgrid, right? The data, the information that these microgrids need to exchange is almost entirely overlapping, whether it's a tactical system, like what they intended it for use in, or a distribution scale microgrid. So we are evaluating the MIL Standard 3071 for use in our installation scale microgrids. It ends up being probably the most complete point schedule that we're aware of for use in that UFGS, which is on the next slide. So it comes up and it's important because of that. So a microgrid control system, UFGS, is a guide specification for microgrid control systems. USACE was required to produce this by December of 2023 in the FY23 NDAA. So we're in the thick of development right now. So it contains all of the definitions of pieces and parts of a microgrid. It has a description of the system itself, of its architecture, what is it intended to do, its purpose. It has some guidance on how do you execute a project, how would you commission a system like this. And then it contains the complete protocol endpoint schedule for microgrid control communication. So this is the main purpose of the document, is to say, this is what a microgrid controller should do. This is what kind of system it serves. This is how you select and design a microgrid controller for the microgrid you're building. We have prioritized, well, to shape our thinking around what goes in the UFGS, we are looking for a conceptual framework that encompasses the different control layers within the microgrid. So primary, secondary, tertiary. I'm sure you guys are all familiar with all of that. But so it's intended to encompass that whole control framework, and it is not supposed to, well, it's supposed to encompass all microgrid sizes, architectures, a lot like the UFC, right? We're not trying to define or bound the size of the microgrid. We're not trying to say, is it distributed? Is it central generation? It's supposed to cover all of them. And it shouldn't rely on specific kinds of distributed energy resources. The UFGS is intended to be technology neutral, right? We are trying to allow for flexibility and adaptability as new technologies emerge, right? It's not going to say you have to use a controller that meets some, again, a lot like the UFC, it's performance-based. If the given controller, whatever is new and developing, meets all of the old performance requirements, right? It's able to do system balancing, then it would meet the requirements of the UFGS. We are working very hard to ensure we comply and acknowledge all of the relevant industry standards, codes, and regulations that are adjacent to microgrid control. So everything from IEEE 1547 and the P2030 7 and 8. There's a whole family of Army UFCs and UFGSs that specify things for like generators and solar panels and distribution systems and substations. And so we have to make sure that we're compliant and consistent with all of those, as well as the microgrid UFC that we just talked about. Its primary purpose is to address communication requirements for microgrid control systems and ensure that we are interoperable between different manufacturers and brands of microgrid control systems. That's kind of the UFGS in a nutshell. I saw a note this morning that Daniel Shepard is not joining us. He would be able to dig into the specifics here a lot better. So I've tried to give a high-level overview, but I was not prepared to speak in detail because Daniel was supposed to be presenting too. So, okay. So we have all of that in the works. We're trying to do our best to develop the tools that we need to solve the problem that we see in front of us, but we also need to recognize that this problem doesn't stand still, right? We are going to experience changes in how our distribution systems need to work. We have new challenges, and all of the electrification requirements we're seeing emerge are going to change how we approach microgrid design and implementation on our installations. This is intended to show a sort of notional installation electric demand curve, where the blue would be what we see today, and the orange and red colors are basically just me kind of throwing out based on lots of different conversations. What are people saying that we might see as we evolve these systems? So, right, we might, as we electrify vehicles, our load curve, it might shift to when people want to charge their vehicles before they go home. We have a lot of housing on our bases, so maybe we see a big uptick in demand when people get home from work. We may add tactical vehicle charging. So there's a lot of work going on right now to electrify tactical vehicles, and the charge requirements for those are not the same as non-tactical, normal vehicles that we see on the streets every day. Some of the vehicles that we talk about, they come in packs of like 15. They need to be able to charge all 15 vehicles in 15 minutes, and they each want to charge at like a megawatt. So that's a huge spike in demand that we have to figure out how to deal with. So again, I don't know exactly what that will look like, but let's imagine, they've been out training all morning, they get home, they're ready to go eat lunch, and they all plug in their electric tactical vehicles at one time, and in 15 minutes they're expecting those puppies to be all charged. So that's going to create some really spiky looking charge demand. Probably the solution is not to just connect them up to the distribution system and say, here is an all you can eat buffet. That's probably not the solution. But, just for the sake of talking about the problem, maybe it looks something like this. Maybe we see a lot of charge demand when missions are complete in the evening, and higher levels of consumption overnight. And then if we electrify all of the loads within our buildings, like this building electrification engineering bulletin we have, we see an overall rise in electric consumption. So microgrids that we design today are not taking into account any of this orange stuff, right? We are only designing microgrids for what we currently see, only for historic data. And so it will be a challenge in the next few years to either figure out how to forecast what this crazy business will look like, or come up with mitigation measures for the microgrids we already designed, right? How are they going to adapt to transportation becoming a critical electrical load? How are they going to adapt to our buildings that support critical missions suddenly having higher electric demand requirements? It's, we have to be thinking about how we're going to solve this now so that we have this solution ready as these impacts begin to be felt. I threw in a couple of research areas that my team looks at just for, I thought they would be of interest. So this is a proposed research program we have. Well, we're developing it as well as trying to pitch it to our internal powers that be for additional consideration. But I talked a couple of times about how our systems exist on closed restricted networks. So the microgrid control or power sensing network is on a separate network from the utility management system is on a separate network from any vehicle charging. And these are physically isolated networks. So how do you exchange data between them to make better control decisions? So the idea here is that we would develop some secure gateway that would manage and interact with each individual system, allowing us to exchange data and controls in a secure way, and give us better visibility at a single point into the whole behavior of our electric delivery system at the installation and where it's being consumed. The other sort of critical component of this is that it has to be able to operate in the same islanded condition as the microgrid, so 14 days without talking to any external system, but also talk to the external system so that you can report data up under normal conditions. That's this connection to this data aggregation. So we're working on kind of the basic development. We want to demonstrate connectivity between a DoD microgrid control system and a utility management system in the next couple of years. All right, I have more about our research portfolio, or I can stop there and do questions, and then we can talk about any of this if it comes up.
Yeah, go ahead and keep going. I think we've got a few minutes left, and then we'll open it up for questions.
Okay, sounds good. So the larger group that I sit in at the lab, Searle, Construction Engineering Research Laboratory, it covers a lot of space in terms of power and energy research for Army installations. So we have folks that work on energy modeling and planning, so being able to develop models that project energy consumption on our installations. There are some of the folks that do these installation energy and water plans, as well as work on developing digital twins of our installations. We have folks that then, they want to aggregate all of the data so that they can perform better analysis. I've included my program there, but VTime is the big, the elephant in the room of energy data and aggregation. So what they're currently doing is looking at various data at rest systems the Army already maintains, whether it's our meter data management system or the Army real property catalog, where we catalog all of the different buildings and real estate that the Army owns, and bringing that all together in a single user interface that folks can access from any installation. Our building energy systems team focuses on building envelope and energy consumption and controls within buildings. My team, resilient electrical distribution systems, where we look at microgrids and power sensing, electrification of our installations, EV integration, all this kind of stuff we've talked about. We have folks that focus on various specific distributed generation technology. Hydrogen and fuel cells are really a prominent research topic for them right now because of the electrification requirement. So if we're not going to use diesel, we're not going to use natural gas, well, hydrogen is sort of the natural way to move, I think. So they are very focused on developing those. And then we have a big waste to energy team. They have some really interesting work in ammonia electrolysis, as well as a big construction project right now of this laboratory called EPIC W2. So that's kind of the overall picture. Within my team, we're trying to evolve our distribution systems to these very flexible and dynamic, optimized, highly visible operations for each installation so that they can react to energy consumption and requirements in real time. Our research portfolio includes work in the resilient electrical distribution systems, which is like microgrids in parentheses, where we work on some control and stability methods. We have a program in trying to develop ways for our distribution systems to automatically build a model of themselves based on control and meter data that we're getting back. It's at this very early stages, so it doesn't really do much at this point, but it's, I think, an important goal for our installations. We do all this work at our installations, but we fund maintenance and sustainment at about 35% usually of what we think is actually required to do the right job. So the more that we can automate, the more that we can take labor-intensive things like one-line validation out of what's required for humans, it can alleviate some of that burden and give us better operating data. So that's what drives the need to try to do something crazy like that. Our power sensing program is using a DoD developed and DoD specific like PMU to assess power quality within our installations and provide some analysis of what's causing power quality problems. It has some like non-intrusive load monitoring objectives as well. And then we have folks working on interoperability. So that tactical microgrid standard is part of the interoperability team. And then they also are working on like generic models of installations for testing and development and validation. So the Corps of Engineers has like 10 research and development priorities. Our team covers 3 of those: resilient installations, secure and reliable energy, and decision making. When we're not doing research, we have our engineering support side where we work on microgrid lifecycle planning, and we're engaged in all of that microgrid implementation work that we talked about under URSIP and the standards and criteria that we talked about in a lot of detail. I think mostly we've already talked about this. I included some of these as like references in the end of the slides, and then the 4 layers of energy resilience, defense, and depth. So that's it. Thank you.
Thank you, Melanie, for that great presentation. To learn more about the Gridwise Architecture Council, go to gridwiseac.org and don't forget to subscribe to our YouTube channel at the link provided.